Hi everyone, welcome to AWM Pitt Grad Seminar. Today we have two speakers with us. Our first speaker name is Katherine Booth. She is a PhD student from Georgia Institute of Technology. And she will be talking today about recovering surface maps from automorphisms of fine curve graphs. Our second speaker name is Marlene Guerrero, and she is an MSc student from University of Puerto Rico. Her topic today, the inhomogeneous diffusion equation of one cell type with discontinuous data. So I would like to ask Katherine, you can go ahead.
Okay, well, thank you so much. I really want to thank the organizers for inviting me to speak. I'm really excited to be here. So there we go. Our sort of main idea for the talk today is that fine curve graphs contain enough information to reconstruct homeomorphisms of surfaces and even get even more information. So first, I'm going to go through sort of some of these terms to make sure that sort of are all on the same page. So when I talk about surfaces, I'm going to be looking at closed, oriented, connected two manifolds with genus G. So the genus G is the number of like holes that you can see in my sort of donuts. And then I'm just looking at the surface, the outside skin. So when you zoom in, it's going to look just like a flat plane. Okay. When I talk about a homeomorphism, I'm going to denote that by homeo of S. These are continuous bijections of my surface with continuous inverses. So I've got a couple examples here. First one on the left is what I might call it point pushing. So you can see I've got a point there and I can push it around. Now, all the points nearby, because I want this to be continuous, are going to also have to push around. And so it can sort of take that purple curve and it's going to have to deform it a little bit. The second type of homeomorphism I might have is if I have sort of an annulus on my surface, I can take it and I can do a nice twist around it. And if I go all the way around so that I can reglue with the identity on the boundary, then I would also still have another continuous map there. Okay, so now we sort of know what homeomorphisms of surfaces are. What are fine curve graphs? So the fine curve graph was originally defined by Bowden, Hensel, and Webb in 2019, and as a tool to use to study diffeomorphisms, which we'll get to a little bit later. But for this talk, we're going to consider it's a graph. It's a graph based on our surface. The vertices are going to be essential, simple, closed curves on our surface. So essential means they're not going to shrink down to a point. Simple means they're not going to self-intersect. And closed means that they're actually going to be loops and not just arcs. So that's going to be the vertices of my graph. And then I'm going to have edges between those vertices when the two curves on my surface are disjoint. Right? So I've got sort of just a small sub graph here. I've got a couple different curves on the left on my surface. You can see like I've got a red curve and a blue curve that are disjoint. And so if I look over at the graph, my red vertex and my blue vertex have an edge between them. But if I look at like my green curve and my yellow curve, those intersect at 2 points. And so those 2 points, the green and the yellow, they do not have an edge between them. Okay, so that's my graph. Now, when I think about if I have a homeomorphism of my surface, what is it going to do to my graph? Sort of the question here. Well, it's going to take every curve to another curve, because I have a nice bijection, that nice continuous bijection. And if two curves started disjoint, they're going to end disjoint. So it's actually going to give me a nice automorphism of my graph. So I have a very natural map. Give me an element of the homeomorphism, it's going to give me an automorphism of this graph. So the question is, can we go the other way? If I give you just any automorphism of the graph, can you recover a homeomorphism of the surface? So it turns out this is the case. This is a result of Long, Margalit, Pham, Verburn, and Yao in 2021, that as long as your genus is big enough, at least two, then this natural map from homeo to the automorphisms of the fine curve graph is actually an isomorphism. Okay, so how do we get from an automorphism of our fine curve graph to a homeomorphism of the surface? Well, I'm going to go through another graph. So I'm going to actually take my graph and I'm going to add in essential curves. So all the curves that do shrink down to a point. And this is going to be called the extended curve graph, extended fine curve graph, which is why I've got that script E. Okay. So I'm going to first start with if I have the curve graph with all of my inessential curves as well, the extended one, how do I get from that to a homeomorphism? Well, I'm going to use something called convergence sequences. So I can take sort of a shrinking sequence of curves that go down to a point, and I can use that to tell me exactly where that point goes after I do my automorphism. Now, if we're thinking just in terms of the graph, looking at this convergent sequence, all the graph sees is a bunch of disjoint curves. So how can I actually make sure that it's going to still shrink down to a point? And the thing is that we have a very specific way to do this. If I think about two curves that are going to intersect infinitely many of the elements of these sequences, they're going to have to go through that middle point. And the two curves that do this are going to have to intersect each other. So that's going to still have to happen after I do my automorphism. And so that's how I know that these are going to still shrink down to a single point. And that's going to tell me exactly where every single point goes on my surface. So that's sort of the second half. How do you get from the extended fine curve graph to the homeomorphisms? But how do I get from, the curve graph to this one that has inessential curves? So the way we do this is with bygone pairs. And so I can take two essential curves, my blue and my red curve, that the only difference between them is this little inessential curve. Okay. And so anytime I sort of mix up my curve graph, my fine curve graph, I'm going to know exactly where my inessential curve is going to have to go because of that. And so that gives me an isomorphism between those two graphs. So that's how I can get from my fine curve graph, my automorphisms of that, and get all the way to a homeomorphism of the surface. All right, so we did homeos. What about diffeomorphisms? That's sort of the natural questions. You figure out something about homeomorphisms. Next step, what happens with diffeo? Because there's a lot of properties that are in same, but some are different. So to start with this, I'm going to just restrict down to C1 diffeomorphisms, which I'm going to denote diff1. So C1 diffeomorphisms are C1 homeomorphisms whose inverse is also C1. So C1 means we have a derivative, and that derivative is continuous. So since we're working with surfaces, really what we have is that our derivatives are these invertible linear maps between the tangent spaces at every point. Okay, so if C1 diffeomorphisms is sort of the thing we're trying to study, what should the graph be? So we had originally the fine curve graph here, which is all the different curves, but this has got a little bit too much wiggle room for the C1 diffeomorphisms, because C1 diffeomorphisms, really the natural thing that they act on is they're going to take C1 curves to other C1 curves. If it's just a C0 curve, I can't. The C1 diffeomorphism is just going to give me another C0. So what I'm going to do is I'm going to restrict to C1 curves. So this is called the C1 curve graph. It's got exactly the same definition, except now we're just working with C1 curves. So essential, simple, closed. We're still on our surface. Edges are still going to be disjointness. So one of the things I've got sort of the curves that I had before, but my purple curve there has got a lot of jaggedy too. He is not C1. He has corners. So he's actually going to be removed from this graph. And we can see that the C1 curve graph is actually a subgraph of the original fine curve graph. All right, so as I said before, the C1 diffeomorphisms really naturally act on this C1 curve graph. Gives you a nice automorphism. So natural question is, can we get back and can we recover all the information and get those C1 diffeomorphisms back? So it's not true. You can't. So LaRue and Wolf in 2022 gave an example of an automorphism of the C1 curve graph that is not a C1 diffeomorphism. And the way that this example works is really messing with that linearity of the tangent space. So what they do is they take lines that are close to slope 1, and they just shift their y values just a little bit in a nice continuous way. And then that breaks our linearity of our tangent spaces, because both your sort of y unit vector and your x unit vector, those are going to go to the identity, but their sum is not going to go to the same place anymore. So we no longer have linear tangent spaces. So what can we do then? Well, what we have is that instead, for any surface, there's this group, which I'm going to call homeo 1 of S, that is properly contains the C1 diffeomorphisms and is also properly contained in the homeomorphisms of the surface that is isomorphic to the C1 curve graph, as long as your genus is at least 2. Okay, so what is what is this group? So just some examples of things from Homeo 1. This is what I call the collapse map. So we're just going to take sort of in polar coordinates, points r theta, and we're going to send it to r squared theta. And so sort of collapses everything down to the origin. And this is going to take every C1 curve to a C1 curve. It's going to give me a nice automorphism of my graph. But the issue comes in is that if you look at what happens to the tangent space, it's no longer invertible. What happens is that if you take any C1 parameterized curve and you actually see what happens after the image, the tangent vectors shrink down to 0. So my whole tangent plane, tangent space shrinks down to a single. Okay, so that's one example. What else can we do? So another thing we can do is this, where we look at where our radius is and we change it, the length of it based on the angle. So on the left-hand side, on the negative x-axis, it's going to be identity. On the positive y-axis, where our theta is 0, we're going to have a magnitude 3 adjustment. And then on the sort of y-axis, we've got pi over 2 and 3 pi over 2. We're going to have a stretching of 2. Okay. So this is definitely not linear in our tangent space, but we're still going to take C1 curves to C1 curves. Now, another thing that I really enjoy about this one is it also messes with C2 curves. So this is the image of x squared, and you can see the oscillating circle from the left has a very small radius, so we have a high curvature, but from the right, we actually have sort of 3 times the size of the oscillating circle, and so a third of the curvature. So it doesn't maps C1 curves to C1 curves, but does not take C2 curves to C2 curves. Okay, so those are a couple of examples from Homeo 1. Now this is a fun non-example. This is a little more complicated formula, which is why I don't have it here. But what it does is it sort of squishes your points, your lines close to the x-axis. You can see those blue ones getting squished, and sort of spreads out the orange ones a little bit. Now this map does take every C1 curve to a C1 curve, but it is not an element of Homeo 1. And one of the main reasons for that is it's not invertible. So if I look, I've got like absolute value of x is sort of between the orange and the blue lines, and that one gets mapped to x squared. And so I have a non-C1 curve getting mapped to a C1 curve. And so if I try to sort of think about inverting this, my inverse is going to be sending a C1 curve to a not C1 curve. So it doesn't give me an automorphism of the graph. It gives me, if I want to think about it in terms of the graph, it does give me a map on the graph, but it is not an invertible map. So there was a couple of examples, but overall, what does Homeo 1 have? So there's a couple of properties that Homeo 1 has. So first of all is that the image of every C1 curve is a C1 curve, as I've been saying, because it's an automorphism of our C1 curve graph. Secondly is that it is a homeomorphism of S. Third is that it's going to preserve tangencies. And what I mean by that is if I have 2 curves A and B that are tangent at a point P, then their images f of A and f of B are going to have to be tangent at f of P. So this is not true for homeomorphisms. You can bend curves all you want and mess up with their tangencies. All right, and finally, so the preserving tangencies, what this does for this is we can think about all of our tangent directions, which is what sort of that space is called the projective tangent space. And so this gives us a nice map, induced map on the projective tangent space, and these maps have to be homeomorphisms. So these are some properties. And so what I want to do for the rest of the talk is just sort of explain how these come from the curve, how we can see these in the curve graph. So the first one just comes straight from the fact that we have an automorphism. We're going to map C1 curves to C1 curves. So that one is pretty much done. Second, being a homeomorphism of the surface. So let's try to look at what we did in the homeomorphism case. Does this work? So convergent sequences are actually going to work nearly identically. We just have slightly less curves that we can choose, but there's still plenty of C1 curves on our surface, and we can still add those inessential curves in and narrow down to points. So that aspect is going to work just fine. But bygone pairs do not work. And the main reason for this is because in the definition of this bygone pairs, we have to make a corner somewhere, either with your essential curves or with your inessential curves. Somebody's going to have a corner and not be C1. And so we have to throw this out. But hope is not all lost. We can have a different workaround. So we can use what's called a one smooth pair. So two different essential curves that are not going to be homotopic to each other, but they will still define that same inessential curve. And we can still sort of get that connection between the C1 curve graph and the extended C1 curve graph. Okay, so we still get a homeomorphism just fine. All right, next one, preserving tangencies. So let's say I have two curves, A and B, that are tangent at a point P. Right? How am I going to be able to tell that after I apply my homeomorphism, my element of homeo 1, that this is going to still be tangent? Because if you just have a homeomorphism, you can take curves that look like this, and then you can make them transverse where they do not have the same tangent direction. The way that we're going to do this is by looking at some more curves, C and D. So C is going to be a curve that is tangent, but just on one side to both A and B. And then D is going to be another curve that's one-sided tangent to both A and B. Now, one-sided tangencies, we're going to have sort of after a homeomorphism, have to have the sort of the same structure, that we have one-sided. And the thing is, if we know that the curves have to be C1, then they have to have the same tangent line at that tangency. And so I get that C is going to have the same tangent line as A and B. D is also going to have the same tangent line as A and B. And so, and same thing, C and D also have to have the same tangent line. So they all have the same tangent line. And so we have to preserve the tangency there. So we have that. All right. Finally, we have getting this induced map on the projective tangent space being a homeomorphism. All right. So to do this, the first thing we need to note is that my map F in homeo 1 and my F inverse are both going to preserve tangencies. And so that means I'm going to have a nice bijection, because I can hit any curve, because the F inverse is going to have to map it from, it's going to send it back to somewhere. It's going to have to come from some other curve. So I'm going to be surjective. And then I'm also going to be injective, because F inverse can only go back to one curve, not two curves. And so each tangent direction is going to have to map to a single tangent direction. Right? So I have this bijection on the projective tangent space. Now, I know the projective tangent space is kind of a mouthful, but really think about, we've got R2 is our tangent space, and I'm looking at all the lines through the origin. So, well, I can think of that exactly as S1, as a circle. Sort of each direction has a slope, and that's going to give me a point on this line. Okay. So what I can do is, if I have two different curves, okay, if I have two different curves, A and B, I can look at my S1, my tangent directions, take a double cover, and get actually 2 points for each. So I've got sort of an A positive direction, an A negative direction, a B minus direction, and a B positive direction. And what I'm going to use with this is that on my circle, if I have two transverse curves, they're always going to have to be opposite, right? So they're going to have to be separated. So A plus and A minus are going to be separated by the B minus and B plus. And similarly, B minus and B plus are going to have to be separated from A minus and A plus. And what this ends up giving us is that we have a bijection on this circle that also preserves the order of how the points are lined out. Okay. And if you have that on S1, a bijection plus preserving your cyclic order, you're going to have to be a homeomorphism. And so we have a homeomorphism on the projective tangent space. All right, so that's our final property. And that's all the things that we were able to sort of recover just from using this graph with the vertices being curves. So I just want to say thank you for your time and the opportunity to speak.
Thank you so much for the talk.